All right, and we're live. Eric, good afternoon, and I have a question if you have a moment.
You shoot.
I was thinking about how we've got all this amazing knowledge that we've acquired in the last several decades on the cosmos, and yet you keep talking about how the pieces still don't quite fit. And I was thinking maybe we could have some examples of how the pieces don't fit.
Sure, I'd be happy to do that. There are a lot of ways in which they don't fit. Einstein clearly described that gravity is due to the space compression of space. And there is no force of gravity. Things fall down not because a force is acting on them, but the space is compressed the closer it gets to the Earth. And as something, you let go of a cup and it gets closer and closer to Earth, it falls through more and more compressed space, and it looks like it's accelerating. It isn't. Great, but Einstein also explained it mathematically, but could not come up with the underlying model process of what is actually going on to do this. Now, mathematics is really intended to describe a phenomenon that you can describe a phenomenon in mathematical terms. I mean, Newton did it. He described his phenomenon in mathematical terms, and he made a strong case for it because we're still teaching it. Now, Einstein could not describe the phenomenon of space contraction could not represent it by a model of a process of what is going on. He only had a mathematical explanation of it. Now, why is that? He's obviously right. There's no question about it. But why can he not describe the process? And the reason for it is because he believed that the process was something working on continuous space, and it isn't. It is working on granular space. And if Einstein accepted the idea of granular space, he would have recognized that in his equation, he thought he was describing a contraction of continuous space, but he actually had the model of granular space. And he had actually uncovered the fact that the universe must be granular. Now,
but he didn't know.
He didn't know it. And in fact, this thing that there was an energy gradient, which means that energy is either increasing or decreasing in some manner within a contracted continuous space, caused people to say, okay, why is it there? We don't know, but how do we moderate it? Well, we can't. They couldn't. For a century, they've been looking for a graviton that fulfills this function, and they can't find it for a very good reason. It isn't there. The contracted space is actually a energy gradient. In other words, when you contract particles of energy, it forms a stronger and stronger energy. And the energy gradient was there, but Einstein was so obsessed with showing that it was contracted continuous space that he basically ignored it. And people twisted themselves into knots trying to explain, if it doesn't do anything, why is it there? Well, it does do something. That is actually the description of space. Now, I can tell you that because we have taken the attitude that continuous space does not exist. Now, along.
So then what is the description of space, as you just said?
Okay, space has to be, it is like, what is the description of a picture in your newspaper? Your picture consists of dots, and what is in between those dots? Nothing.
Yeah.
I mean, there's newsprint there, but it doesn't have to be. If you could remove the dots from it, it would still show you the picture. It doesn't really need the newsprint as a backing. And continuous space is something like insisting that the picture in the newspaper must have a backing, a continuous backing, a piece of paper. It doesn't need it.
Wow.
And
That's a great metaphor.
That is exactly the same idea. But in the cosmos, there are points in space, we call them nodes for reasons that we describe in the book. And between the nodes, there is nothing. There is a void. And the void is not empty space, because empty space is space that could have something in it, but doesn't at the moment. Like an empty chair is a chair, but it has nobody in it, so it's an empty chair. In the same sense, space is not like a chair. You know, there's nothing there. It's not like there's a chair there, nobody is in it. There's just nothing there for anybody to get into. And when Alan Turing decided to ask a very interesting question, which is, if space is continuous, there must be some mathematical procedure that would describe any point on a continuous line.
Right.
And if it isn't continuous, what happens? You can describe a picture by where there is a dot, but between the pictures, you really cannot describe that space that between the dots. In other words, if you have a void, you cannot find a mathematical procedure that will describe a point there, because there can't be any points there. There can't be any mathematical procedure for something that is a void, has nothing in it, doesn't have an empty chair. There's nothing there. And what he found is that a line, be it just a line you draw on a piece of paper, or the path followed by a photon of light or some other energy, it mostly consists of points for which you cannot find any mathematical procedure to identify where that point is. It's not that we haven't found such a thing. Such a thing cannot possibly exist. Claiming that it does exist leads to a self-contradiction, which means that it doesn't exist. So Turing found it, Einstein found it. Turing didn't realize what he had discovered. He published it in the journals of mathematics. I don't think he made any attempt to put it into cosmology, and I don't think any cosmologists looked at it seriously, because they would have realized it immediately. He was describing a bunch of widely separated points which had a vacuum between them, and you cannot find any mathematical procedure to describe the location of something in a vacuum, because there's nothing there to describe. Now, these are two completely different ways that two different people basically discovered the same thing. Right. Einstein did it without realizing it. He was so, I don't want to say obsessed, but he was so certain about the fact that space must be continuous that he said, all right, this gradient must be in a compressed space. Well, that gradient describes a compressed space,
Yeah.
but it describes it in granular form. And
but he was set in his
he was
assumption of continuity as his framework.
He was set.
He wasn't able to get outside of it.
Exactly. And he wasn't the only one.
Oh, sure, of course.
Everybody in his generation was set in the concept of continuity. We are set in our concept of continuity, but yet we know, if we look at it, that this is something in our state of mind. It's our mind that takes discrete images and makes it look continuous. Now, it's harmless in human life, so big deal. You think it's continuous. Well, you think the action of a movie is continuous. You think your action on the television is continuous. You believe the action you see with your own eyes is continuous. None of them are continuous. They are discrete frames that go fast enough that the brain can put them together and sort of fill out the voids between them.
Create the illusion of
crazy illusion of continuity, and it's harmless. The problem is, if you take this harmless human illusion and transfer it to cosmology, it is no longer harmless.
Because the cosmos has no awareness of our illusions.
Exactly. The cosmos doesn't give a damn. And it is full with these things. We have the illusion that photons of light can either be particles or be waves. Now, if they were particles, and the light propagates on its own volition, it ain't ever going to leave the sun. So it must leave the sun as a wave. And when it gets to Earth, it must change back to a particle in some cases and not in other cases. Now, if you believe that, you'll believe anything. But we are forced into that belief because in continuity, light must travel on its own volition. The alternative is something either travels because it has the energy, or there is something else propelling it. But in the smooth and continuous universe, you cannot have a propulsion system. In a granular universe, you can. You can think.
Maybe we should save that distinction for another session.
We can save that.
That might be a good place to
start. But I mean, there are. I came up with like a dozen of these without even trying very hard.
It's great.
And they are all things that are explainable, but not in the context of a continuous universe.
So if we just let that go, a lot of the puzzle pieces can begin to fit.
Well, I think they do. And the reader is going to have to make a decision. Do enough of the pieces that didn't fit before fit for him to believe in this, or doesn't he? Does he still believe in continuity?
Or at least consider it as an alternative.
I'll consider it as an alternative.
All right, what fun.